So now a nice way to think about naive Bayes and the contribution of each feature is to illustrate it in such a diagram where we say, okay, given, so we first have the prior probabilities. What's the likelihood of any document being about sports, about murder mystery, or about automotive? We see that automotive is highest. And then we weigh in all the features that we have. For example, all the individual words that we focused on in our feature engineering part. So we said maybe those are the 10 words that we're interested in. And then for each of those features, we check what is the probability of the label, what's the probability that the label is automotive, given that the word is run, for example. What's the probability that the word is run given the label murder mystery? What's the label that the word run occurs given that is a sports document? And then we see the probability of the sports document is the highest. And we multiply all the features. So each feature makes its contribution. And when we multiply all of this together, we get our final likelihood. And in this case, we would say the document is most likely about sports, and all the other categories are less likely. So we would classify this document as being about sports. Now there's one final thing that we want to remind you of. And this is like zero counts and smoothing. So how do we actually calculate the probability of the feature given the label? So there's a simple formula that is based exactly on the definition. So the definition was the probability of A given B is the probability of A and B divided by the probability of B. So we would actually count how many times does the label co-occur with the feature. So if the feature is the word run, we would say how often do sports document contain the label, the word run. So let's say this is 1,000 times. And we say that there are 10,000 sports documents, so 1,000 divided by 10,000 is like 10% is the probability that we have the word run in a sport document. The one problem that we have is what happens if a feature never occurs. For example, let's say, the particular rare name or a rare word never occurs. So if that happens, if this is the case, then we will have here that the count F and label is 0, right? And if it's 0, then this whole probability is 0, right? Because we have a 0 here divided by something that's still 0. And this also means that the whole probability becomes 0 because we have a multiplication of probabilities. If one of them is 0, then all the probabilities are 0. For example, we could have that the probability of, well, actually that should be the other way around, of sports given this feature becomes 0 because one of those probabilities for a rare word becomes actually 0, right? So what we typically do is something called smoothing, which is also, which means that we basically we never allow zeros, right? So we would add a small epsilon to each count, to each value here, so that we don't get 0 values here and we get a positive term instead. And if we have positive term, then the probabilities never get 0. And we can assign all possible labels to all possible features. And actually this makes a lot of sense because especially if we have little data and our training data is very small, then it's very likely that we will have 0 counts. That's something just never happened. But this is not because it doesn't co-occur in reality, but it's just because we have so little data, right? And it's never reasonable and realistic to give a probability of 0 to any event. So we would always have a small probability that we should assign to any event. Good, so this was naive Bayes. My assessment you've already heard. I think naive Bayes is not something that you should try out in practice. However, something that you should definitely try out is deep learning. So this is the current state of the art. It's also a very old field, invented in the 1940s. But then it had ups and downs, and since the last 10 years at least, it's the lead paradigm, so everyone's using deep learning. So deep learning is a subfield of machine learning that is inspired by the human brain. So the original metaphor was we have neurons in our human brain, they're somehow connected, and this gives a network, right? And this deep learning was previously also called artificial neural network. So we have a network of neurons and somehow mimics the brains. And those nodes and those units in the network, so the little dots, the little balls here, they are also called neurons. If you have this brain metaphor in the head, or you can also call them units. If you want to generalize a little bit and see it in a more abstract way. And those connections are called connections or weights. Now, one of the first neural networks was this one here. It's also called the Perceptron. The basic idea is it is a network that doesn't have any hidden layer. And I'll show you in a second what a hidden layer means. But how does it actually work? So it takes certain inputs. So this is again a feature representation with n inputs of a certain input. So this could be a text or a document or something. Then connected with each input is a weight. So we have n weights here. And there's a special input, but I don't want to talk too much about this. So there's a constant value of 1, and it also has a weight b. What we're going to forget about this in the further slides is basically this is called a bias weight, and it gives you one additional weight that you can learn. So your model becomes a little bit more expressive, but it's not so important fundamentally. So what we then do is we do a weighted sum of the input. So each input is a number here. And we weight up those numbers by the weights that we have, plus this bias term here. And then we get a sum, right? And on top of this sum, we have a nonlinear function. This is also called an activation function or nonlinearity. And then this gives out a real number, let's say 0, 1 or minus 1, 0.5, whatever. So it gives some activation. And the basic original idea of this whole concept was that there's a brain neuron in our head, and if it's the things that connect to it have certain values, and if the way and if how those inputs are weighted take a certain direction, then this neuron is going to fire. So originally the activation was a threshold function 0, 1 or 0 and minus 1. And the idea was if this weighted sum here that's a pre-activation exceeds a certain threshold, let's say 0, it's bigger than 0, then the neuron fires, it's activated, it's on, otherwise it's off. If the input is too small, the weighted input is too small, then there's no activation. Good, we can also have, instead of only having one input, we can also have multiple, instead of having one output. So here we had just one output, have multiple output, and then we have, instead of having like here, this is like a dot product, this is like a vector x times multiplied by a weight vector. Here we have, and yeah, so we have the x vector multiplied by the y vector. So this is the dot product. And in this case, we would have a vector matrix multiplication of the input times this weight matrix. And of course, and then the interesting part comes when we do not have, when we have some hidden layers, right? Here in this case, now we have hidden layers, and those hidden layers are actually what make the neuron powerful. And this is also then called a multi-layer perceptron or feed-forward network. And in terms of terminology, as I've already said, those things here, those balls, those dots are called, they have multiple names, one of them being node, if you think about it in the network. Unit is also an abstract name, or neuron, right? They can also be called neuron. And we have many neurons. We have some are, this is an input neuron, these are two output neurons. all the neurons that are organized on the same level are also called a layer. So we have an input layer, we have one hidden layer, another hidden layer, and then we have an output layer. We have the activation functions, right? So we have different activation functions here, and we have weight matrices, and not only one, but we have 3 different weight matrices. In a simplified visualization, this is also what you see often. We don't depict the individual neurons, but we just depict the layers. And if you want to perceive of this in terms of mathematical notation, so then what is our first layer computing? It's computing the input times this weight matrix, x times w, and then we add this bias vector. But as I said, we can omit this, and then this gives a vector. This is a vector times a matrix. This gives a vector. We apply our nonlinearity on top of this thing. Now in the first slide, with the perceptron, we only had this once, but if we have multiple units here, multiple units in the next layer, then we need to apply our activation function on each individual element of this vector. And the second layer is doing the same calculation actually. However, instead of taking the input as the original input, what's coming into the network, the feature representation, it takes the value of the hidden layer as input, right? And then it's doing the same computation, and you can do a forward computation all throughout the network. What kind of activation functions are there? First of all, the activation functions are very important. You need non-linearities, otherwise you get a linear model, which are not so powerful. But as soon as you have this activation function, you get a non-linear model, and those non-linear models are really powerful. They're universal approximators, so we need this non-linearity. And most of those activation functions, they are attached to a neuron, right? And they map real number to a real number. So you can assume each neuron, each unit, each node has a pre-activation, and then applying this activation function gives an activation. And typically they were originally designed, as you see here, to be like a 0-1 function. So basically the node is activated, it's firing. So if it has a value of 1 here, or it's not firing, right? If it has a value of 0 or -1, right, then it's not firing. So this was the original idea. But then over time, people thought, okay, we can also have different forms, such as the ReLU function, which has a different shape. And then we can even generalize this and get different shapes. But the original is like, it was like on-off. Each neuron could be on-off. Later on, people use different activation functions, which may have nicer properties. There's also a special activation function, softmax, which we're not going to talk about in this course now in terms of mathematics, but this is often the activation function that is used for the output layer, of a neural network. So you have a multi-layer perceptron. The last layer takes a softmax activation function, and then this means like if you have 5 output neurons in the last layer, the softmax makes a probability distribution out of it. So the first neuron has like 20% probability, second has 10%, etc., and it should add up to 1. And this can then be interpreted as the first class having 20% probability, second class having 30% probability, etc. Let's make a small example. Let's say the input to our neural network is the vector 1, 0.5, -2. So where does this come from? We don't know. So this is just like now the assumption. This could be some representation of a sentence, for example, that we get from there's some magic that provides us with this. And then we have a weight matrix that we now set to 1, 0, -1, -1, 10, and -9. Where do we get this weight matrix from? Well, essentially the first weight matrix is initialized by us, so we can set it randomly. Afterwards, it's being trained on the data. So we do some training algorithm, and the weight matrix results out of this magical algorithm. And let's assume we have this sigmoid activation function. Which one is this? This is this one here, which takes 0 and 1 as limit values, and only if the input is very small, it's between 0 and 1, otherwise it goes to 0 and to 1. So what we do is, what's the output of our network? We do x times w. This is an input vector times a matrix. And what is the result? If you remember our linear algebra from school or from university, we have like 1.5 minus 0.2 multiplied by this 3×2 matrix. So what do we get? So here, first, what's the output shape? This is 1×3, 3×2. So we got a 1×2 vector as output. Let's compute this minus 19.5 here. This is 1 times 1 is 1. Then we have 0.5 times minus 1, this is minus 0.5. So we have 0.5 now. And to 0.5, we add minus 20, because minus 2 times 10 is minus 20. So we have minus 19.5. And similarly, we calculate the 17.5 here. Now, what is the sigmoid applied to a vector of size 2? Where it's the sigmoid applied on each of the on each of the elements of the vectors? And what is sigmoid of minus 19.5? Let's look here in the graph. Well, here's minus 10. It goes to minus 20. It's pretty, very, very close to 0. And if we go to 17.5, that's going to be very, very close to 1. So actually, I just wrote for simplicity, I do some rounding here, and the output of our network would be 0. Okay, what's the high-level view? The high-level view is neural networks are mathematical functions of the form. So we have like a linear product, the input times weight matrix and nonlinearity applied. Then we feed this in to the second layer, which takes this as input, multiplies by the weight matrix, applies another nonlinearity, and we can apply more nonlinearities, more layers if we have more layers. X is given as input, G and F are our activation functions. W and V is what we want to learn. And we define a loss function. Now, this is already a little bit advanced for this course now, but just as a high-level overview, well, we have our neural network for a certain input, and we have certain training data. So we have the inputs associated with labels. We want to maximize. We want to check the squared difference of our network from the labels. X, Y is our training data. Theta, our parameters. This is the weight matrices, right? So we have this loss, and then we want to minimize this loss. So we want to optimize our parameters, our weight matrix, such that the loss becomes minimized. That's called the learning. So basically, we want to set the weight parameters such that our neural networks predicts the true labels in a good sense, in the sense that the squared distance to the true labels is minimized. That's a high-level overview. How do we do this? With an algorithm that's called backpropagation, which is the scope of an advanced lecture on deep learning for natural language processing. Good, what are further aspects? So the one important aspect is how do we get the input representation? And that's something we haven't discussed about in this lecture. We're going to discuss about this in lecture number 13. In general, we are using something called embeddings, if you've heard about that. Those are dense vector representations of words. So we have, to each word, we associate a vector. And empirically, those embeddings have properties that are very appealing, namely that similar words in an intuitive sense, like cat and dog are similar. They also have similar embeddings. That's something very powerful and very something that we desire, because if similar objects have similar representations, then well, those representations are actually useful, and they help us to generalize, even to things that we haven't seen, because representation is similar. So our network can hopefully generalize. And those embeddings are also derived from another neural network. So in the first step, we would first derive embeddings, and then in the second step, we would feed those embeddings into another network. Good, what are libraries for deep learning? There's Keras, TensorFlow, PyTorch, and in the lecture, in the exercise, we're going to use Keras, and there's many more in-depth tutorials on deep learning on YouTube and other platforms, which you can have a look at. And if you do anything in natural language processing nowadays, your first choice would be neural networks. Good. Let me finally just quickly talk about scikit-learn, which is a machine learning library which isn't used so often for neural networks, but in general it's used as a machine learning toolkit. It has a Python library with many implementations of machine learning algorithms. Unlike NLTK, it has no focus on NLP, but it's more general and much more widely used. So I never use NLTK, but I do use scikit-learn. There's installation, documentation, and a book if you want to go for this. So how could we play around with this? There are certain data sets. For example, we have pictures. We want to classify what kind of flowers those pictures are based on the length and the width of the leaves. So we would say from scikit-learn, import data sets, and then get me the iris data set. And then we could print a description. I guess those are certain descriptions. Probably they're not going to look like pictures. We can also check out what are the feature names in this iris data set. And the feature names are septal length, septal width, petal length, petal width. So, I mean, I'm not going to explain all of those things here. They're also not important in terms of content-wise, but you see there are 4 features that characterize each flower. And what we do here next is where we print out some random points in the data set. So these are some random flowers. That's flower number 0, for example. It has like a feature representation. Like there are 4 features. These are the feature lengths of this particular flower. And then what is actually the label for this flower that's represented as a 4-dimensional vector, where it's flower number 0, which has the name Setosa, right? Then we would split our data into train, def, and test. And let me also just rewrite this here. So we would take the iris data sets together with the iris labels. We're going to merge that, make a list out of it, shuffle the data set. As we said, we need to take that randomly. Take the first 20 points as the training set, 80 points as the def set, and the rest as the test set. And then the inputs, we just keep the inputs in the training data, and the training labels, we just keep the labels. And in the def set, which here is called def test for some weird reason. So that's never used by anyone, but for some reason that's used in the book or in those slides here. We have the def test, and we do the same. We split the labels from the data itself. And we use a naive Bayes classifier. And we call that Gaussian naive Bayes. So we say this is our classifier, Gaussian naive Bayes. We train the classifier on the training data with the training labels. And then we predict our classifier on the def set. We make a prediction and we compare that to the gold, and you see it's pretty good here. There's some misclassifications outlined here. And we can also evaluate the results. We say, give us a metric. So we calculate the accuracy. Accuracy is 91%. And we can also compute the precision, just using precision score, recall score, F1 score for each of our labels. So I see there are 3 labels, and the precision for each of those classes is like given here, the recall is given here, and also the F1 score is here, from which we see that the model is doing actually pretty well for the Setosa class. Obviously, that is a simple flower to classify, and the others are slightly worse. We can also do a, what's that? That's actually the same thing. In a different in a different format. So obviously there's a classification report which gives out all those numbers at once without doing it separately. And it also gives us the support. The support is the number of instances which have a certain label. So in total, we have 80 instances in this data set. So obviously that's the test data set. And we can also print a confusion matrix in a similar manner. Of course, you can try out other classifiers in scikit-learn, not only naive Bayes, but also support vector classifier, random forest classifier. Random forest is a good classifier. So this is like one of the stronger ones. Support vector classification, also one of the stronger ones. Even though, as I said, sklearn doesn't feature, it isn't too good at neural networks, and neural networks typically beat most of the other classifiers that are typically included in sklearn. Good, so you can also compare now the classifiers here, though this is like an interesting thing. SVM is not very good in this case. In this case, okay, so this is a support vector machine classifier which performs good, but if you choose different parameterizations of this classifier, then it performs considerably worse. So the tuning is important, right? The features and the hyperparameters. Good. Try around further with sklearn. That's certainly good, but also do the homework and learn Keras, which is even better than sklearn, at least if you want to use neural networks. The take-home messages, we had two things. The first one was the evaluation. We said cross-validation is a good thing in terms of data sparsity. We then had two evaluation metrics. The one was accuracy. We said it's not good for imbalanced data set. And we resorted to precision recall and the combination of those two in the F1 measure. Finally, we had the machine learning data sets where we had 3 different classifiers. And the 3 different classifiers were decision trees, naive Bayes, and the deep learning, where I would always give the preference. The first one that you should try out is deep learning. Then if you want to try out decision trees for interpretability, that's also a good idea. And if you want to get not so good results, you finally have the option to also try out naive Bayes. Finally, try out scikit-learn as a library, which is very useful. It has nice built-in metrics. That's what I use it for. So when I want to calculate the F1 score or something similar, I use scikit-learn. And try out Keras if you want to do deep learning. And that's what you can do in the homeworks. So why is that useful, what we learned today? We can use that for many classification tasks. So here are a couple of classification tasks. Readability assessment is a classification task. Is this book suitable for children aged whatever? So that's a binary decision, maybe. Sentiment analysis, where you would judge whether a tweet is positive or negative. Nowadays, more important than sentiment analysis, for example, you want to classify if something is toxic, if a comment on a social media platform such as Twitter is toxic, should we ban that? Is that this tweet discriminate against women, against foreigners, for example? That's something that could be a potentially very useful classifier. We also have word segmentation, where we have a word like bank, and we want to classify which class is it, right? Is it like class number 0? Is it class number 1? Is it the financial institution or the river bank? And there are many, many, many more classification tasks in natural language processing. Classification is one of the most important tasks in NLP and in general data science and machine learning. Good, so here's the link to the book, and see you in the next lecture.